Swift and functional programming. Many languages inspired how Swift was implemented, and though Swift is an object-oriented language, it has taken many ideas from functional programming languages like Haskell and Scala. This isn't a book about functional programming, but understanding the basic parts that Swift has taken from the functional programming paradigm will make your Swift code even better. Immutability. The core of functional programming, other than functions themselves, is immutability. Being able to differ between mutable and immutable values is commonplace in many object-oriented languages as well. Immutability can seem like an over-the-top constraint on your code, especially given that the result of most applications is the mutation of state. For example, interacting with a database or changing the properties of your user interface requires mutation. Much of the core business logic in your application can be written using immutable values, though. One of the hardest places for developers to use immutability is a collection of data, such as an array. You'll often find yourself wanting to perform different mutating changes on an array, such as adding new values, transforming the values in the array into new values, or filtering out values that don't match certain criteria. Many of these actions also require mutable variables, for example, a counter in a loop. Many imperative programming techniques have taught us to rely heavily on mutable state. In Swift, instead of mutating a variable or its value, you create a new immutable value by using the old value. Consider the benefit you get from using an immutable array. If you create a new immutable array based on the values in the old immutable array, you can be sure that the values in the old array won't change. They're immutable, so it's safe to use them as a reference for your new array. Swift takes care of this for you. In addition, you get the benefit of the compiler's ability to make great performance enhancements because it doesn't have to deal with mutable values. Immutability is core to the following topic: pure functions. Pure functions. A pure function, given the same input, always gives the same output. It doesn't have any side effects like printing to the screen or changing a database. Pure functions especially don't mutate their input or use any global state to determine their output. They're pure in the sense that they do their job and don't interact with the world around them. Take a second to think about this concept. Imagine if the majority of your application was made up of pure functions. How hard would it be to rationalize about what your application was doing? It wouldn't be hard at all, and that's the point. You may be surprised that because pure functions are so ridiculously simple to comprehend, the majority of the time you can look at a function's name, parameter types, and return type and work out exactly what it does. After getting used to this, you can sometimes tell what a function does just from the types, without even looking at the name. This is where functional programming and mathematics begin their journey together. You can trust math. It's reliable at a whole new level. With that in mind, I want to mention a trait of functions in mathematics. They're pure. Think of functions like sine, cosine, and tangent. In math, these functions are trusted completely, and for a good reason. They always give the same output when given the same input, and they never mess with the result of your calculations. First-class and higher-order functions. Functions and methods are important in many languages. The issue is that they're only seen as important because they encapsulate logic. This mindset is completely removed in the functional programming paradigm. Swift can treat functions as first-class citizens, which means functions can be passed around like data. This can be done with defined functions as well as anonymous functions, which are called closures. Having this ability is incredibly important because it allows you to do something further with your functions. Create functions that take functions or return functions. A higher order function is the next level of a pure function. These higher order functions do one or both of two things. Take one or more functions as input and output a function. Having first-class functions and the ability to use higher-order functions allows you to create incredibly dynamic, easily understood code. Depending on your past experience, you may have seen these in other languages like Ruby or JavaScript with blocks and anonymous functions. Or, as an example of a higher-order function, you may have used the map, which takes a list of values and maps them to a new list of new values. Recursion. The trusty loop, whether it's a while or for loop or one of their relatives, is a core part of imperative programming and therefore most object-oriented programming as well. This isn't the case in functional programming. Instead, recursive functions are used. A recursive function calls itself within its definition. The most famous of these is the function used to calculate Fibonacci sequences. To calculate a Fibonacci number, you add the Fibonacci number of the input minus 1 to the Fibonacci number of the input minus 2. The function is recursive because it calls itself from within its definition. But listing 1.9 also defines that when the fib function is passed 0, it returns 0, and when it's passed 1, it returns 1. These are the base cases, the seed values. Without these seed values, the recursion would never end. When crafting a recursive function, it's common to consider these base cases before you begin to write the recursive part. Doing this leads to much simpler functions. Let's take listing 110 as an example. This pseudocode sums the numbers in an array using recursion instead of a loop, which is what you may be used to jumping straight to. This function defines two base cases that return 0 if there's nothing in the array, or if there's one item in the array, return that item. For example, calling sum of the empty set returns 0 because there's nothing to sum, and calling sum 3 returns 3 because the sum of all the values in the array is 3. There's only one value in the array, 3. What about this head and tail thing, though? What is that? The head is the first element in the array, and the tail is everything that isn't the head. By looking at an array like this, recursion becomes easy. Calling sum of 1, 2, 3 expands to 1 plus sum 2, 3, which expands out to 1 plus 2 plus sum 3. The base case says that when there's just one value, it should be returned. So the full expression is 1 plus 2 plus 3, which gives you 6, just as expected. Why not use a loop? It comes back to trusting mathematics and pure functions. Nowhere in either fib or sum is there any mutable state, unlike in a loop, where a variable would keep track of the current sum and change on each iteration of the loop. Without state, and by being thoughtful about how you construct recursive functions, you end up with code that can be optimized better, rationalized about more easily, and tested more easily. And best of all, you can create lots of smaller functions or use higher order functions to reuse code more effectively and keep your code lean as your application requirements grow. The last thing I need to mention about functional programming techniques is concurrency. Without mutable state, everything you've read so far can work more effectively in a multi-threaded environment, which iOS is. I didn't mention concurrency until now because it's largely the focus of why people should use functional programming techniques. Focusing solely on that takes away from the beauty of applying your trust of mathematics to your programming. Trusting your code is more important than concurrency issues. The type system. Strongly typed languages are a mainstay when it comes to trusting your code, and this is doubly true in Swift. It has a powerful and strict compiler, although, as demonstrated earlier, it's not as overbearing as some languages. You may wonder why I'm mentioning the type system in a section about functional programming. Functions have input and output types, of course, but that's not a big deal, unless you stop to think about the fact that the types in the parameters and return value define a new type. For example, you may have a function that takes two objects of the same type as its parameters and returns a Boolean. You're likely to assume that the function compares the two objects. The type definition of the function has some meaning, and that's why Swift has type definitions for functions. This one would then be some class, bool. You'll learn more about this later. This is important for functional programming because it means you can restrict the kinds of functions passed into higher order functions. Using map as an example, any function that's passed to map should take a collection of values and return a collection of values. It wouldn't make sense to pass the function I described before into map, so Swift won't let you do it. It treats the types for the input and output of your functions as a type definition. This way, you can define the type of function your higher order function accepts, just as you define the type of input any function will accept. Summary. As a language, Swift has made programming for iOS a much more approachable idea. Many developers who were scared off by Objective-C are flocking to Swift because it's more familiar to them. In the past few pages, you've learned about many of Swift's improvements versus Objective-C, its safety features, and some of the niceties Swift has for you as a developer. You've also learned about some of the basic concepts Swift takes from functional programming languages to allow you to write safer code that's easier to rationalize about. In this chapter, you've read a lot about Swift, which is expected. After all, this is a book about Swift. What I haven't discussed, but you'll learn about throughout this book, is the fact that Swift isn't the only tool Apple has given us to make things easier and to help us be more effective developers. Xcode 6 and many of its features help us greatly too. You'll soon see how Swift enables you to be a Swift developer. Understanding the tools you'll use to build iOS applications, such as Xcode 6, is the focus of the next chapter. You'll begin to use tools like Interface Builder, work your way around Xcode 6, and start learning about the auto layout system.